On April 17, 2025, NASA released an announcement that quietly reshaped humanity's place in the universe. It was not framed as a declaration of alien life, nor accompanied by dramatic press conferences or sweeping claims. Instead, it arrived in the careful language of science, data, spectra, atmospheric signatures. But within that restraint was something extraordinary. On a planet known as K2-18b, located 124 light years from Earth, astronomers detected chemical compounds in the planet's atmosphere that, on Earth, are produced exclusively by living organisms. Not trace amounts, not marginal hints, concentrations nearly 1,000 times higher than what exists naturally on our own planet. If these molecules truly originate from biological processes, then this distant world may host not just life, but a biosphere rich enough to reshape our understanding of biology itself. And while confirmation remains cautious, conservative, and methodical, the implications are unmistakable. Humanity may be standing at the threshold of its first verified discovery of life beyond Earth. But as that realization begins to settle, another question immediately follows, a deeper one. If life exists elsewhere, what does it actually look like? Astrobiology has long wrestled with this problem. Life on Earth represents only one successful solution to existence, shaped by specific chemistry, gravity, temperature, and history. There is no guarantee that life elsewhere resembles anything we recognize. To explore this unknown, scientists build theoretical models grounded in physics, chemistry, and evolutionary principles, attempting to imagine organisms that could survive in environments wildly different from our own. The Milky Way alone contains more than 100 billion stars, and conservative estimates suggest that most of them host planets. Beyond our galaxy lie hundreds of billions more galaxies, each containing their own countless worlds. The total number of planets in the observable universe is so vast that the human mind struggles to comprehend it. Against that backdrop, the idea that life arose only once seems increasingly implausible. And yet, despite decades of searching, not a single unambiguous piece of direct evidence has yet been found. No microbial fossils, no cellular signatures, no organisms caught in the act of living beyond Earth. But absence of evidence is not evidence of absence. Many scientists now believe that discovery of extraterrestrial life is not a question of if, but when. To accelerate that search, NASA is developing the Habitable Worlds Observatory, a next-generation space telescope designed to survey nearby stars and identify at least 25 potentially habitable exoplanets. Its mission is not merely to find worlds like Earth, but to analyze their atmospheres for chemical imbalances that suggest life. Launch is planned for the early 2040s, and its capabilities may exceed anything humanity has ever deployed into space. While that future approaches, scientists continue to imagine what life elsewhere might be like using what we already know. On Earth, life began in water. 4 billion years ago, the first cells formed in the planet's oceans, protected from radiation and temperature extremes. It is therefore natural to begin with the concept of a true ocean world. TOI 1452b is one such candidate. Located roughly 100 light years away, it is about 1.5 times the size of Earth and nearly 5 times more massive. What makes it extraordinary is its composition. Roughly 30% of its mass is liquid water. That is not 30% surface coverage, but 30% of the entire planet's mass. This means TOI 1452b contains approximately 7,000 times more water than Earth. This is not a world with oceans. It is a world that is an ocean. No continents, no exposed land, just an unbroken planet-wide sea. In such an environment, evolution would follow familiar yet unfamiliar paths. Convergent evolution tells us that similar environments tend to produce similar forms, even when organisms arise independently. Fish, Dolphins, and ancient marine reptiles all evolved streamlined bodies because water demands efficiency. TOI 1452b. Active swimmers would likely develop elongated shapes optimized for movement through dense liquid. But size changes everything. Gravity on TOI 1452b is slightly stronger than Earth's, but in water, gravity is softened. Buoyancy supports mass. This opens the door to truly colossal life forms. Creatures hundreds of feet long, dwarfing Earth's largest whales, could exist without collapsing under their own weight. Some might reach lengths of 2 or even 300 feet. Their bodies could resemble living torpedoes, with complex internal anatomy and external structures unknown on Earth. A massive dorsal fin might rise along their backs, not for stabilization, but as a biological sensor or communication organ. Such a structure could emit pulses of light, creating a language of flashes and rhythms across the ocean's vast darkness. Energy demands for such giants would be immense. Feeding alone might not suffice. Evolution could favor organisms whose skin functions as a living solar collector, capturing light from their star and converting it directly into bioelectrical energy. In this way, sunlight would supplement metabolism, powering movement, cognition, and communication. Yet the strangest life would likely exist far below the surface. On Earth, even at the crushing depths of the Mariana Trench, life persists under pressures exceeding 1,000 atmospheres. TOI 1452, B's ocean could extend tens of miles deep, with pressures surpassing 8,000 atmospheres. In such conditions, rigid structures would fail, bones would shatter, shells would collapse. Deep sea organisms there would likely be soft, elastic, and densely packed with fluid-filled tissues resistant to compression. Eyes would be useless in eternal darkness. Instead, life would rely on vibration, chemistry, electromagnetic sensing, or pressure waves. Some might glow, not as decoration, but as a tool. Bioluminescence would become language, lure, and weapon. And beyond water worlds lie even stranger possibilities. In 1976, Carl Sagan and Edwin Salpeter proposed that life might exist not on solid surfaces, but suspended in the clouds of gas giants. Coro 9b, a massive gas giant more than 1,000 light-years away, may provide such an environment. While the planet's depths are hellish, its upper atmosphere is comparatively calm. Temperatures range from -25 to 150 degrees Celsius. Pressures are manageable. Complex organic molecules may exist. In these skies, life would never touch ground. It would drift, float, hover. Entire ecosystems could exist in layers, organisms living their entire existence in motion, unaware of the crushing inferno far below. These creatures might resemble enormous balloons or biological airships, their bodies made of thin membranes filled with lighter gases. Sunlight could be absorbed across their surfaces, powering exotic forms of photosynthesis. Radiation would be countered through pigments that convert harmful energy into harmless glow. Some of these beings could grow unimaginably large. Carl Sagan suggested that the largest could span nearly a mile. Their central organs alone might rival skyscrapers in size, drifting like living continents through alien skies. Other worlds challenge life in different ways. LHS 1140b is heavier than Earth, with gravity twice as strong. Life there would move slowly, heavily, supported by thick limbs and dense musculature. Flight would be impossible. Bodies would be squat, compact, and resilient. In colder versions of such worlds, metabolism would slow to near hibernation, organisms entering states of suspended animation for survival. Conversely, low-gravity worlds like TRAPPIST-1d could produce terrifying abundance. With gravity far weaker than Earth's, life could grow to monstrous scale. Predators hundreds of feet tall, flying creatures the size of passenger jets, forests of trees reaching skyscraper heights, a world ruled by hunger, scale, and relentless competition. But even all of these forms assume one thing in common: carbon. Life as we know it depends on carbon's unique bonding properties. Yet carbon may not be the only path. Researchers have identified hundreds of autocatalytic chemical reactions that do not involve carbon. Silicon, a close chemical relative, can form complex chains under the right conditions. On worlds like Kepler 62f, silicon-based life could arise. Such organisms would not be soft, they would be crystalline, bodies made of silicates, growth resembling mineral accretion rather than reproduction, memory encoded not in DNA, but in lattice structure and atomic patterning. To human eyes, they might appear as living statues, rocks that move too slowly to notice, or angular beings with reflective armor and sharp geometry. Some might be passive, others aggressive. Intelligence could emerge in forms utterly incompatible with our assumptions. And beyond biology lies technology. If life evolves long enough, intelligence arises. If intelligence persists, technology accelerates. To understand how far this can go, astronomers use the Kardashev scale, which classifies civilizations by their energy consumption. Humanity remains a Type 0 civilization, barely beginning to harness planetary energy. A Type 1 civilization controls the full energy output of its planet. A Type 2 controls its star. A Type 3 controls its galaxy. Type 2 civilizations could build Dyson swarms, enclosing stars in vast energy-harvesting structures. Type 3 civilizations could rearrange galaxies, manipulate black holes, and reshape cosmic structure itself. Beyond that lie hypothetical Type 4 and Type 5 civilizations, capable of manipulating universes or dimensions themselves. Despite searching, humanity has found no clear evidence of such civilizations. This contradiction is known as the Fermi paradox. The universe is vast. Life should be common. So where is everyone? Perhaps we are early. Perhaps we are late. Perhaps advanced civilizations hide. Perhaps they move beyond detectability. Perhaps they already passed through this galaxy billions of years ago and are gone. Or perhaps the universe is filled with intelligence waiting quietly, observing, allowing young civilizations like ours to grow before revealing themselves. As humanity stands at the edge of discovery, one truth remains. Whether we find life tomorrow or 1,000 years from now, the universe is far stranger, richer, and more alive than we once believed. And we are only beginning to learn how to look.